Hello everyone, and welcome back to the channel. Today, we're embarking on a truly mind-bending journey, a thought experiment that delves into the very fabric of reality. We're going to explore a question that has fascinated scientists and philosophers alike. What would happen if gravity, the fundamental force that orchestrates the cosmic dance, suddenly and completely disappeared? Now, I want to emphasize right from the start that this is a purely hypothetical scenario. Gravity is not a force that can be switched on or off. It's an intrinsic property of the universe, deeply intertwined with spacetime itself. But by exploring this what if, by imagining a universe without gravity, we can gain an unparalleled appreciation for the delicate balance that governs our existence, from the grandest cosmic structures down to the smallest particles. Our understanding of gravity has undergone a dramatic evolution over the centuries. It's a story of human curiosity, ingenuity, and the relentless pursuit of knowledge. Let's start with the ancients. Aristotle, the influential Greek philosopher, believed that objects fell to earth because they were seeking their natural place. Heavier objects, he thought, fell faster because they had a stronger desire to reach this natural state. This geocentric view, with Earth at the center of the universe, dominated scientific thought for nearly 2 millennia. Then came the scientific revolution. Nicholas Copernicus challenged the geocentric model, placing the sun at the center of the solar system. Galileo Galilei, through his meticulous observations and experiments with inclined planes, began to unravel the true nature of motion and gravity, although he didn't fully understand the force that causes it. It was Sir Isaac Newton, in the late 17th century, who truly revolutionized our understanding of gravity. Legend has it that he was inspired by watching an apple fall from a tree. Whether the apple actually hit his head is up for debate. Newton formulated his law of universal gravitation, which states that every particle in the universe attracts every other particle with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This was a monumental breakthrough. Newton's law explained not only why apples fall to the ground but also the motion of the moon around the earth, the planets around the sun, and even the tides. It was a universal law, applicable everywhere in the cosmos. But Newton's theory, while incredibly successful, had its limitations. It couldn't fully explain certain subtle anomalies in the orbit of Mercury, for example. Enter Albert Einstein. In the early 20th century, Einstein unveiled his theory of general relativity, which completely redefined gravity. Einstein proposed that gravity is not a force in the traditional sense, but rather a curvature or warping of spacetime caused by the presence of mass and energy. Imagine a bowling ball placed on a stretched rubber sheet. It creates a dip, a curvature in the sheet. That's what massive objects do to spacetime. Other objects then move along the geodesics, the shortest paths in this curved spacetime, which we perceive as the effect of gravity. General relativity was a radical departure from Newtonian physics. It accurately predicted the bending of starlight around the sun, a phenomenon observed during a solar eclipse in 1919, which provided strong evidence for Einstein's theory. Now, in the realm of modern physics, we're striving to unify gravity with the other fundamental forces of nature, electromagnetism, the strong nuclear force, and the weak nuclear force. These other forces are described by quantum field theories, which treat forces as being mediated by fundamental particles. For example, the electromagnetic force is carried by photons, the strong force by gluons, and the weak force by W and Z bosons. The quest is to find a quantum theory of gravity, one that might involve a hypothetical particle called the graviton. Finding the graviton and developing a quantum theory of gravity is one of the biggest challenges in modern physics. It could lead to a theory of everything, a single framework that describes all the forces and particles in the universe. But for our thought experiment, the precise nature of gravity, whether it's a classical force, a curvature of spacetime, or something mediated by gravitons, isn't crucial. What matters is that it's the dominant force on large scales, shaping the universe as we know it. Let's take a moment to marvel at the sheer scale and beauty of the universe, all held together by gravity. Our solar system, with its 8 planets, and dwarf planets, asteroids, and comets, is a gravitationally bound system, with the sun's immense gravity dictating the dance of all these celestial bodies. Our sun, in turn, is just one of hundreds of billions of stars that make up the Milky Way galaxy. These stars, along with gas, dust, and dark matter, are all gravitationally bound, swirling around the galactic center, where a supermassive black hole resides. And our Milky Way is not alone. It's part of the local group, a collection of over 50 galaxies, all gravitationally interacting. And the local group is part of the Virgo supercluster, a vast structure containing thousands of galaxies. This intricate cosmic web, stretching across billions of light-years, is a testament to gravity's power and reach. It's gravity that sculpted the universe from the primordial fluctuations after the Big Bang, pulling matter together to form stars, galaxies, and the vast structures we observe today. Now, let's zoom in from the cosmic scale to our own planet, Earth. Gravity's influence here is not just fundamental, it's essential for life itself. It's gravity that keeps our feet firmly planted on the ground, allowing us to walk, run, and build civilizations. It's gravity that holds our atmosphere, a delicate blanket of gases, including the oxygen we breathe, close to the planet. Without it, our air would simply dissipate into space. Our oceans, rivers, and lakes are all held in place by gravity. It's gravity that drives the water cycle, the continuous movement of water from the oceans to the atmosphere to the land and back again, a process vital for life. Even the Earth's internal structure is governed by gravity. The immense pressure in the Earth's core, generated by the weight of the overlying layers, creates the intense heat that drives plate tectonics. This movement of the Earth's crust creates mountains, recycles nutrients, and regulates our planet's long-term climate. Now, for the heart of our thought experiment. Let's imagine that, in a single, universe-altering instant, gravity vanishes. Not weakens, but completely disappears. What would unfold? We'll examine the consequences in detail, starting with the immediate effects on Earth and then expanding our view to the solar system, the galaxy, and the universe as a whole. The moment gravity disappears, the consequences on Earth would be immediate and catastrophic. Everything not firmly anchored to the ground would become instantly weightless. But this wouldn't be the gentle floating you experience in an airplane. Due to the Earth's rotation, objects would be flung outwards, away from the planet's surface. As our subarticles highlighted, the Earth spins fastest at the equator, with a rotational speed of roughly 1,000 miles per hour, 1,600 kilometers per hour. This means that the outward centrifugal force would be strongest there. Our atmosphere, no longer held down by gravity, would rapidly expand into the vacuum of space. This would cause an instantaneous and catastrophic drop in air pressure. The human body is not designed to withstand such a sudden change in pressure. As one of our subarticles described, our inner ears would rupture, causing intense pain and disorientation. The air in our lungs would expand violently, potentially causing them to burst. Moreover, the gases dissolved in our blood, primarily nitrogen, would come out of solution, forming bubbles in a process called ebullition. This is similar to what happens when a diver ascends too quickly, leading to decompression sickness or the bends. In this case, however, it would be far more severe and rapid. Blood vessels could rupture, and vital organs would be severely damaged. We'd likely lose consciousness within about 15 seconds due to lack of oxygen to the brain. Death would follow within minutes, a terrifying and agonizing end. And what about the water on our planet? The oceans, lakes, and rivers, no longer restrained by gravity, would also be flung outwards. Imagine colossal, miles-high waves of water, no longer confined to their basins, rising into the sky and forming gigantic, swirling globules before dissipating into the vacuum of space. The sight would be both awe-inspiring and utterly terrifying. With the loss of atmospheric pressure, any remaining liquid water on the surface would quickly boil away, even at low temperatures. Earth would become a dry, barren, and airless husk in a remarkably short time. The devastation wouldn't be limited to the surface. The Earth's internal structure is a delicate balance between the inward pull of gravity and the outward pressure generated by the incredibly hot and dense core. Without gravity, this balance would be shattered. The immense pressure in the core, no longer counteracted by gravity, would cause the planet to expand rapidly. This wouldn't be a gentle swelling. It would be a catastrophic expansion, triggering earthquakes and volcanic eruptions of unimaginable intensity. The ground would crack and buckle. Massive fissures would open up, swallowing entire cities. Mountains would crumble as the underlying tectonic plates, no longer held in place, shifted violently. Molten rock from the Earth's mantle would surge to the surface, engulfing everything in its path. As the sub-articles mentioned, the Earth wouldn't necessarily explode instantly, but the expansion would be significant enough to cause unimaginable destruction, turning the planet's surface into a hellscape of fire, rock, and debris. The Earth's rotation would also play a role. As the planet expands, its rotational speed might change, potentially leading to even more violent stresses and strains on the crust. Ultimately, the Earth, no longer held together by gravity, would begin to break apart. Large chunks of the planet's crust and mantle would be flung outwards, joining the chaotic mix of debris in space. The once blue planet would become a collection of scattered fragments, a testament to gravity's crucial role in maintaining planetary integrity. The chaos wouldn't be confined to Earth. The entire solar system, a beautifully orchestrated gravitational dance billions of years in the making, would be thrown into disarray. The planets, no longer held in their elliptical orbits by the sun's gravity, would fly off in straight lines, following their tangential velocity at the moment gravity vanished. Mercury and Venus, being closer to the sun and moving faster in their orbits, might be flung out of the solar system entirely, becoming rogue planets wandering through interstellar space. Mars, Jupiter, Saturn, Uranus, and Neptune would similarly embark on their own solitary journeys. The gas giants, Jupiter and Saturn, with their immense mass and rapid rotation, might experience even more dramatic internal disruptions than Earth as their internal pressures are unleashed. The asteroid belt, a region between Mars and Jupiter containing millions of rocky bodies, would also be disrupted. These asteroids, no longer held in place by the combined gravity of the Sun and Jupiter, would scatter, some being ejected from the solar system, others becoming potential hazards for the remaining planets on their new, unpredictable paths. The Moon, Earth's constant companion, would also drift away, its familiar face receding into the darkness. The tides, which are caused by the Moon's gravitational pull, would cease, further disrupting Earth's already devastated ecosystems, if any life remained. The Sun, the heart of our solar system, is a giant ball of mostly hydrogen and helium, a nuclear fusion reactor held in equilibrium by a delicate balance between gravity and outward pressure. In the Sun's core, immense gravitational pressure forces hydrogen atoms to fuse together, forming helium and releasing tremendous amounts of energy in the process. This outward pressure from fusion is what prevents the Sun from collapsing under its own gravity. Without gravity, this delicate balance would be instantly shattered. The Sun's core, no longer compressed by gravity, would rapidly decompress. The rate of nuclear fusion would become uncontrolled, leading to a runaway thermonuclear explosion. The Sun would expand dramatically, engulfing the orbits of Mercury, Venus, and possibly even Earth, if it hadn't already escaped. It would become a red giant, but only briefly. The expansion would be so rapid and violent that the Sun would quickly explode in a spectacular supernova, one of the most energetic events in the universe. This supernova explosion would scatter heavy elements, forged in the Sun's core over billions of years, throughout the surrounding space. These elements are the building blocks of planets, stars, and even life itself. So, in a sense, the Sun's death would sow the seeds for future generations of stars and planets, although in a vastly different, gravity-less universe. The supernova would also send out a powerful shockwave, a blast of energy and particles traveling at near-light speeds. This shockwave could potentially interact with the remaining planets in the solar system, further disrupting their trajectories or even destroying them altogether. The Sun is just one of hundreds of billions of stars in our Milky Way galaxy. And each of these stars is a similar ball of gas, held together by gravity and powered by nuclear fusion. If gravity were to disappear universally, every star in the Milky Way, and in every other galaxy throughout the cosmos, would suffer the same fate as our Sun, a catastrophic supernova explosion. The night sky, currently a serene tapestry of twinkling stars, would transform into a breathtaking but terrifying spectacle of exploding stars. The universe would be filled with brilliant flashes of light, as billions upon billions of stars meet their explosive end. Galaxies themselves are held together by the combined gravitational pull of their stars, interstellar gas and dust, and a mysterious substance called dark matter. Dark matter, which doesn't interact with light, makes up the majority of the mass in galaxies and plays a crucial role in their structure and stability. Without gravity, galaxies would lose their structural integrity. The beautiful spiral arms of galaxies like our own would dissolve, and the overall shape and structure of galaxies would be lost. Even the supermassive black holes that reside at the centers of most galaxies might not survive this cosmic unraveling. While our understanding of black holes in a gravity-less universe is incomplete, some theories suggest that they might become unstable and evaporate or even explode, releasing the immense amounts of matter and energy they've accumulated over their lifetimes. This process, known as Hawking radiation, named after the late Stephen Hawking, is thought to occur even under normal circumstances, but it might be dramatically accelerated in the absence of gravity. So, what would be the ultimate fate of a universe without gravity? After the initial chaos of exploding stars, disintegrating planets, and dissolving galaxies, what would be left? The universe would likely become a vast, cold, and incredibly diffuse expanse. The fundamental building blocks of matter, atoms and molecules, would be scattered throughout space, drifting aimlessly without any force to bind them together. The intricate structures we observe today, stars, planets, galaxies, and clusters, would be gone. The universe would lose its organization, its complexity, its beauty. It would become a homogeneous soup of particles, with no stars to illuminate the darkness, no planets to harbor life, and no galaxies to provide a sense of cosmic scale. Without gravity to clump matter, there is no light, no stars, no planets, and no life. There is nothing. This journey into a gravity-less universe has been a dramatic and perhaps unsettling thought experiment, but it serves a crucial purpose. It highlights the profound importance of gravity, not just as a force that keeps our feet on the ground, but as the fundamental force that shapes the cosmos, drives the evolution of stars and galaxies, and makes life itself possible. Thank you for joining me on this mind-expanding exploration of a universe without gravity. If you enjoyed this video, please give it a thumbs up, subscribe to the channel for more deep dives into the mysteries of the cosmos, and hit that notification bell so you don't miss our next adventure.